Inorganic Chemistry, Chapter 5. This will be the last lecture on this chapter on transition metals. We're going to look at valence bond theory applied to transition metals in coordination compounds. Let's flash back and remember what we learned regarding valence bond theory applied to the A group elements, the non-transition metals. We said that covalent bonds are formed usually between two atoms by the overlap of two half-filled, singly occupied orbitals of the bonding atoms. For example, we have a hydrogen atom with a half-filled orbital, one electron, overlapping with another hydrogen atom with a half-filled orbital, forming a shared pair of electrons, and we call that a covalent bond. Now, for transition metals, we treat it differently. Valence bond theory treats metals to ligand donor group bonds, and we're talking here about transition metal coordination compounds. We treat them as coordinate covalent bonds. When a filled orbital of a donor atom overlaps with an empty orbital of a central metal atom or cation, we can successfully predict geometry using VESPR. That works. One stipulation here is the number of ligands joining to the central cation determines the geometry, whereas non-bonding electrons that are already on the central metal are ignored. This is because the non-bonding electrons are on the inner shell, and they're believed to have little effect on molecular geometry. We'll only consider one example of valence bond theory applied to transition metals, and I'll explain why in just a minute, but here it is. Here's a coordination complex diamine silver cation complex. The electron configuration of silver element is S1d10, and the electron configuration of silver cation would therefore be S0d10. So here is the ground state electron configuration of a silver plus 1 cation, 4d10. The S and P orbitals are empty. Along come two amines, two ammonia molecules. They want to donate into empty orbitals because they each bring a pair of electrons. So valence bond theory says, okay, we need two empty orbitals. Let's mix together. One S and one P will get two sp orbitals times 2. Here they are. And each ammonia molecule can donate a pair of electrons into it, forming the bond. And that works. On page 185, we saw that for A group compounds, valence bond theory successfully predicts the 3D structure. That's useful. And molecular formulas gives us the ratio of atoms combining. Well, we could use valence bond theory to explain the bonding that we know occurs in coordination complexes, but the problem is it's really not predictive at all. It can't predict the coordination number of complexes that might form. Nor can it explain other properties such as colors or magnetic properties, which we'll look at in a moment. As a result, other bonding theories have been developed. There's crystal field theory and molecular orbital theory. And these have their limitations, but they are more predictive, more powerful than valence bond theory. So we're going to go ahead and talk about crystal field theory in this course. I won't get into molecular orbital theory. You'll cover some of that in a later organic course, and if you go on in university and take inorganic chemistry, they'll go in greater detail. First, let's look at the colors of transition metal solutions. These are coordination complexes. Look at the array of colors. Look at vanadium, 4 different oxidation states, each with its own color. Chromium, 3 different oxidation states, 3 different colors. What is all the color arising from? Note that A group elements typically are colorless, whereas transition metal complexes are often colored. Why is that? Before we get into the whys, let's talk about color itself. Page 186. So, white light consists of electromagnetic radiation ranging from approximately 400 to approximately 750 nanometers. There's no sharp beginning and start. It's a gradual change. On the low end, we get into the ultraviolet over here, ultraviolet and infrared up here. And these are outside the normal range of vision of humans. Now, although white contains a rainbow of colors, our eyes, the eyes of humans, are only sensitive to three primary colors: red, green, and blue. When we see white light, what we are seeing is a mixture of all the colors as the superposition of red, green, and blue. If one or more of the colors of white light is removed or absorbed, the light of the remaining colors is what passes to our eyes. And based on the proportion of RGB remaining, your brain interprets the color. Red, green, and blue are known as primary colors of light. And the combination of two or three primary colors of light produce the secondary colors of light. Take a look at the color wheel on the right here as I describe this. The secondary colors are yellow, formed by a mixture of red and green; magenta, formed by the mixture of red and blue; and cyan, formed by the mixture of blue and green. And when all three are combined, we get white light. Let's consider reflected light. In the upper left diagram, a substance appears black when it absorbs all the colors of light that are incident upon it. So no light is escaping, it appears black. Look at the top right here. A substance appears white when it scatters all colors of light, assuming that all colors of light are incident upon it. Look at the lower left. A substance appears yellow when it absorbs all the colors except yellow, so only yellow light is being reflected here. But there's another way that a substance can appear yellow in the lower right here. A substance may also appear yellow if it absorbs only the complementary color of yellow. That is indigo in this case. So if every other color is being reflected except indigo, that mixture in our eyes appears yellow. Page 187. See the test tube containing a blue liquid? What makes it blue? Many chemical solutions, such as those of transition metals, absorb specific colors or wavelengths of light. And the mixture of wavelengths that are not absorbed are transmitted, and they are called the complementary colors of what is absorbed. What is transmitted is what we can see. So in the solution in the test tube, it's the red and the orange that are being absorbed. The other colors, the complementary colors of red and orange, are what's being transmitted, and our eyes blends those to see blue. We can say that blue is a combination of the complementary colors of red and orange. Here's a table of complementary colors. For example, light of a wavelength of 410 nanometers is violet, and its complementary color is yellow. If we move to 480 nanometers, that color of light is blue. Its complementary color is orange. At 530 nanometers, green light has a complementary color of purple, and so on. So here's an instrument that we use in the lab that measures the intensity of light at various wavelengths. It's called an absorption spectrometer. Here's a basic illustration. We have an electromagnetic radiation source emitting a variety of wavelengths. We choose a narrow slit and direct it towards a prism or a transmission diffraction grating, which splits the light into whatever wavelengths are present, and it divides them. It has an exit slit with a narrow opening that will choose one particular wavelength of all of the wavelengths that are split by the prism or diffraction grating, and directs that particular wavelength through a sample of our solution in a cuvette. So light that is not absorbed, that is transmitted through the solution, is incident upon a detector, a photovoltaic cell that produces electricity as photons hit it. Photons of light release electrons, current, and the intensity of the current is directly related to the number of photons that pass through the sample and hit the detector. and the number of photons that are incident upon the detector depends upon the concentration of the analyte in solution. The greater the concentration of analyte, the less will be the amount of light transmitted, and the greater will be the amount of light absorbed by the sample. Even before we measure the concentration of analyte in solution by directing a single wavelength of light through it, we sequentially direct all wavelengths of visible light through a sample solution. And the intensity of light of each wavelength is plotted on what's called an absorption spectrum, as you see below. So here is the absorption spectrum of copper-2 ion. So all the wavelengths of light are sequentially passed through the solution, and we have a plot on the y-axis of the amount of light absorbed. And you can see that light is absorbed at many wavelengths, but particularly in the red section, which is the complementary color of blue. So here on page 188 we see the absorption spectra of 7 different transition metal cations. They're superimposed. Now the color that you see is the color that would appear to the observer. These would be the complementary colors. And notice that they absorb at many different wavelengths, but the maximum wavelength of absorption is indicated by the highest point, and that's the wavelength that is most strongly absorbed by that particular ion. So the visible absorption spectrum of clear samples can be determined by scanning with a visible spectrophotometer. Clear simply means transparent. It means that light from an image would pass through undistorted and we'd see a clear image. So this solution of copper-2 sulfate is clear blue. This beaker of water is clear and colorless, but both of these are clear. Clear does not mean colorless. This obviously is not clear. This suspension is turbid. Take a look at this graph below. For a solution of hexa-aqua titanium 2 cation, which appears purple to our eyes, here is the absorption spectra. These are the wavelengths of light incident upon it, and this is the relative absorbance at each wavelength. In the visible spectrum, between say 400 and 800-ish, the wavelength of maximum absorption is referred to as lambda max. So lambda is the Greek letter L, this is lowercase l, and we use it in chemistry to refer to wavelength. Lambda max is the wavelength of maximum absorption. Now a particular species can have multiple wavelengths at which it absorbs strongly. Lambda max is the strongest, and this in the visible region, hence lambda max. Problem 8. The presence of partially filled d orbitals is usually necessary for color, which we will explain in a moment. But given that, explain why potassium cation and strontium cation are usually colorless. Well, the question is, do they have partially filled d orbitals? What about aluminum 3 and tin 4? Well, it's an easy question to answer. Take a look at the electron configurations of potassium. Here's potassium is 4s1, 3d0. Potassium cation would simply be 4s0, and it would have no electrons in the d orbitals, so it's not colorful. Likewise with strontium, strontium 2 would be 5s0. The d orbitals are empty. The same case can be made for things such as aluminum. Aluminum plus 3 would have empty s and p orbitals. And in the case of tin plus 4, well, it would be 5s0, 5p0, and its d orbitals are filled, they're not partially filled. We need to have partially filled d orbitals to give rise to color. So on page 189, let's take a look at crystal field theory, CFT, which proposes that ligands, that would be Lewis bases, electron donors, will donate pairs of electrons to empty orbitals of the transition metal or its cation. In the illustration below, we see ammonia with a non-bonded pair of electrons donating into an empty orbital from a metal, forming what's called a coordinate covalent bond or a dative bond. The d electrons of the transition metal are not involved. They're not used to form the bond. It's the ligand that provides both electrons to form this coordinate covalent bond. The ligand donate their electrons into empty d orbitals or s or p orbitals in the next highest period. Previously we looked at the shapes of the d orbitals, but now we have to look at them more closely. So take a look at the dxy orbital. Notice that there are 4 lobes in which electrons can move, and these lobes lie in the xy plane. Now notice also that they are not directly on the x or y axis, but between the xy axis. Similarly, the dyz orbital has lobes or electron density in the yz plane, but again not on the y or the z axis, but rather in between them. The dxz orbital has lobes where electrons can reside in the xz plane, but again between and not on the x or z axes. Now look at the dx squared minus y squared orbital. Compare it to the dxy orbital. Notice that it also has electron density in the xy plane, but in this case the electron density is right immediately superimposed on the xy axis. And finally we have the dz squared orbital, which has most of its electron density right along the z axis with a small ring of electron density in the xy plane. So when these orbitals have electrons in them, they become electron clouds. Now in the free transition metal, like in the elements, all 5 of the d orbitals are degenerate. They are of the same energy. But as soon as they form compounds or complexes, that changes. According to crystal field theory, the repulsion between the d electrons and the electron pairs of the ligands causes a destabilization of the d orbitals, and the energies become higher, becomes more unstable, more reactive. And electrons in various d orbitals are not affected the same. And the color, this is the key, the color of transition metal complexes arises from the absorption of visible light as electrons undergo transitions from one d orbital to another. Now the energy gap between d orbitals in transition metal complexes is very small. It's in the same energy range as the photons of visible light, and you probably know that visible light is a low energy form of electromagnetic radiation. Hopefully it is, because we're exposed to it 24/7. So in fact it's a low energy light, and the energy gap between these d orbitals, although they're somewhat different, they are close enough together that their energy gap is of the same magnitude as visible light. Take a look at problem 9. Aqueous solutions of chromium 2 chloride are blue, chromium 3 chloride are green, potassium chromate are yellow, and potassium dichromate are orange. Explain why these solutions have different colors. You can appreciate that these different compounds of chromium have a different number of atoms bonded to chromium through its d orbitals. And this creates a difference in the energy of the d orbitals between the different compounds. Hence, different wavelengths of light, different energies of photons will be absorbed in the different compounds. So let's get to the details of crystal field theory. Now, we mentioned previously that coordination complexes of transition metals can have anywhere from 2 to 12 ligands bonded to the central metal cation. Pretty overwhelming. The most common situations are 2, 4, or 6 ligands, and that's all we're going to deal with in this course. And if we have 6 ligands, we'd have an octahedral field, if you recall. So when you have 6 electron clouds in 3-dimensional space, the farthest they can get from each other is in an octahedral arrangement, if you recall from valence bond theory. So in the diagram on the left, these ligands are represented by black dots, and the d orbitals are represented by the egg-shaped lobes. There are 6 black dots arranged octahedrally around the central metal cation. Crystal field theory proposes that in an octahedral field, the 6 ligands approach the nucleus directly along the x, y, and z axes. And this would cause the greatest repulsion of transition metal orbitals that lie right along the x, y, and z axes, such as the dx squared minus y squared and dz squared orbitals. So look again at the shapes of the dx squared minus y squared and dz squared orbitals, which have most of their electron density right along the x, y, and z axis. So not surprisingly, electron density in these orbitals will be most repelled by the 6 ligands coming in to the central metal cation. So as a result, the orbital energy split, with 2 d orbitals higher in energy than the other 3. The splitting is called the crystal field effect. The difference in energy between it is called the crystal field splitting energy, delta for difference. In an octahedral field, it's designated delta sub O for octahedral. And the 2 high energy orbitals are called EG orbitals. They're renamed. And the 3 lower energy orbitals are renamed, and they're called T2G. They get new names. So picture here the degenerate 5 d orbitals in the element. Then in the presence of ligands, there is repulsion, and overall the energy of those d orbitals increases, but they are not equitable, they're not equal. Those lying exactly on the x, y, and z axis are most repelled. Those between the axes are least repelled. D electrons occupying the T2G orbitals will stabilize or lower the energy of the complex, even though they're not involved in bonding. Whereas d electrons occupying EG orbitals would tend to destabilize or raise the energy of the complex because they repel the ligands coming in to bond. The magnitude of the octahedral field splitting energy depends upon the strength of the ligand. So ligands that donate strongly are called strong field ligands, and they create a large crystal field splitting energy. Ligands that donate weakly are called weak field ligands, and they would create a small energy gap. Here on page 191, we see the relative strength of ligands. So moving from left to right, ligands become better and better electron donors. Notice the sequence is not consistent with basicity. So ammonia and even water are less basic than, say, hydroxide, and yet ammonia and water are better electron donors, better ligands with respect to transition metal cations. Nevertheless, we can see from the table that ligands such as cyanide and ammonia and thiocyanate and carbon monoxide are strong electron donors. We call them strong field ligands, whereas water and hydroxide and fluoride and chloride and bromide and iodide and so on are weak electron donors. We call them weak field ligands. We can appreciate the importance of the difference of the strength of different ligands in the next example. Let's start here with cobalt plus 3. Electron configuration. And for these, you'll want to refer to the tables in your notes on page 171. So here is cobalt, the element, cobalt, 4s2 3d7. We're going to take a look at cobalt plus 3. Electron configuration is S0d6. Here's cobalt plus 3, S0d6. This is the ground state electron configuration. In COF6-3, and I want to point out to you that in the notes, this 3 is cut off. It should be -3. COF6-3, aka hexa fluoro cobaltate 3. Let's compare that with this other octahedral complex, hexaamine cobalt 3. Now, we've got two different ligands here. Ammonia, if you recall, look up here, ammonia is a strong ligand, whereas fluoride is a weak ligand. What difference does that make? Ammonia donates its electrons to the metal orbitals more readily than electronegative fluoride. Well, because it's more electronegative, it holds on to its electrons more strongly. The crystal field splitting energy generated by these strong ammonia ligands is so large. See the difference here? Here's the large crystal field splitting energy due to the strong ligand versus the small crystal field splitting energy due to the weak ligand. So the crystal field splitting energy generated by the ammonia ligand is so large that the d electrons of the metal will all move to the lower T2G orbitals, even though pairing energy resists. Remember Hund's rule? So electrons repel each other. They would like to spread out as far as possible. The energy gap with a strong ligand is so large that it's as if these were two different orbitals, and the electrons will all fill the lower energy T2G orbitals before they fill the EG orbitals. The octahedral field splitting energy is greater than the pairing energy repulsion. Thus, hexaamine cobalt 3 is predicted to be found in a diamagnetic low spin state. Do you recall diamagnetic means that there are no unpaired electrons? And we call that a low spin state with fewer unpaired electrons. A high spin state would have more unpaired electrons. Now compare that. The crystal field splitting energy generated by the fluoride ligands is so small, see how small it is here, that the d electrons of the metal will remain in their original orbitals because the pairing repulsion is greater than the splitting energy. So the octahedral field splitting energy is small. It's less than the pairing repulsion, and therefore the electrons spread out, as you see, as far as possible from each other. And thus, hexafluorocobaltate 3 is predicted and found to be paramagnetic. Paramagnetic, if you recall, means that there is at least one unpaired electron. And this state is called a high spin state. Here's an example. This is hexa aqua iron 2 complex. It's hexa coordinate. It's got 6 ligands, and they're weak. Water is a weak ligand, so we would expect an octahedral coordination complex in which the octahedral field splitting energy would be small, and the electrons would spread out over all of the d orbitals, giving rise to a paramagnetic compound with a high spin state. We'll look at some particular examples on the next page which will make this clear to you. Page 192. High and low spin configurations of some ions in octahedral complexes. This will take shape as we go through this. So titanium 3 has a D1 electron configuration. Now, I'm just giving you these, but you can refer back at any time. Let's see, scandium, titanium, here it is. Titanium 3 is a D1 electron configuration. Let's place those d electrons in the octahedral field orbitals Eg and T2G. So there's one electron in the T2G orbital. The magnetic property is either going to be paramagnetic or diamagnetic. If there are one or more unpaired electrons, it's described as being paramagnetic. The electron configuration is written as T2G1 Eg0. just like we'd say S2P2. Now we can't really describe this as being low spin or high spin because it can only have one electron configuration. We don't differentiate between low and high spins until we get to 4 electrons or more, as you will see. Let's apply this to an octahedral complex in which the transition metal has 2 d electrons. Examples would be titanium 2 and vanadium 3. Those 2 electrons would simply fill the lowest energy orbitals. They would spread out according to Hund's rule because of pairing repulsion. The magnetic property is still paramagnetic. The electronic configuration would be written as T2G2EG0. Let's try an octahedral complex with 6 ligands, and the central metal cation has 3 d electrons, such as in vanadium 2 or chromium 3. Those 3 electrons would simply spread out evenly across the T2G low energy orbitals. The magnetic property is paramagnetic. The electron configuration would be written as T2G3EG0. If we had an octahedral complex in which the transition metal has 4 d electrons, then we need to consider the strength of the ligand. If we have weak ligands like water or fluoride or bromide, then the octahedral field splitting energy is very small and the pairing energy is greater than the field splitting energy, and the electrons will simply spread out as if all the orbitals were degenerate. This condition, we see it's paramagnetic. This is, note, it's called, up here, this is called a high spin state. The electron configuration would be written as T2G3EG1. If, however, you had a strong ligand creating a large octahedral field splitting energy, there would be a large gap between the EG and T2G. That energy gap is greater than the pairing repulsion, and so the electrons would be forced to stay in the T2G orbitals. And this would be still paramagnetic. T2G4 EG0 is the electron configuration in that case. So when you have 4 or more d electrons on the transition metal in an octahedral field, depending on the strength of the ligand, the octahedral field splitting energy will be small, in which case we get high spin state structures. Otherwise, with a strong ligand, the octahedral field splitting energy is large and we get low spin states where there are fewer unpaired electrons and more paired electrons. Consider now with 5 d electrons in an octahedral field. Examples would be manganese 2, iridium plus 4. Again, in a high spin state, meaning with weak ligands, small crystal field splitting energy, electrons simply spread out. Surely that's paramagnetic. The electron configuration is T2G3EG2. However, with strong ligands like cyanide or ammonia, a large crystal field splitting energy occurs, and electrons will pair up rather than spread out. So all 5 electrons move into or stay in the T2G orbitals. It's still paramagnetic because we have at least one unpaired electron. This electron configuration is T2G5EG0. With 6 d electrons in an octahedral field, consider weak ligands where there's only a small octahedral field splitting energy. Those 6 electrons will spread out as far as they can, and now they have to start pairing up. It's still paramagnetic. The electron configuration is T2G4EG2. 4 plus 2 is 6 valence electrons. If we had strong ligands that created a large crystal field splitting energy, all 6 electrons would be forced to remain in the low energy T2G orbitals, all paired up. This is now diamagnetic. Electron configuration T2G6EG. 0. About 7 d electrons in an octahedral field with a small field splitting energy because there are weak ligands. 2, 3, 4, 5, 6, 7. That's called a high spin state. They're not paired up as much as they can be. Clearly it's paramagnetic. We would describe that as T2G5, Eg2. 5 plus 2 is 7. With strong ligands and a large octahedral field splitting energy, 1, 2, 3, 4, 5, 6, and finally 7 here. This is now paramagnetic again, T2G6, Eg1. Once you get to 8 through 10, there really only is one possibility. They're all considered to be high spin states. Once you get to 8 or more electrons, you only have one possible electron configuration, and all of these are considered or named high spin states. There's no pairing that's really forced here. So palladium 2, platinum 2, 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. It's paramagnetic, T2G6, Eg2, 6 plus 2 is 8, and there's no other possibility here. So with a total of 8 electrons, regardless of whether the ligand is strong or weak, regardless of whether the octahedral field splitting energy is large or small, you're going to wind up with the same electron configuration. 6 electrons in the T2G orbitals and 2 in the Eg orbitals, and they'll all be paramagnetic. So we don't differentiate, we'll just say they're all high spin states. With 9 electrons, as in copper 2, similar to the last case, regardless of the order of filling, they're all going to wind up being paramagnetic, T2G6, Eg3. 6 plus 3 is 9. And finally, for D10 configurations like silver or 1 or cadmium 2, you can see that all 5 orbitals will be filled, regardless of the strength of the ligand, regardless of the octahedral field splitting energy. They're all going to be diamagnetic, T2G6, Eg4. 6 plus 4 makes 10. Let's try problem 11. For the following coordination complexes, name the coordination complex, draw labeled d orbital diagram showing electron configuration, write out the d orbital electron configuration, state whether it is paramagnetic or diamagnetic, and its spin state is being high or low. First one here, Cr, Co taken 6 times plus 2. Cr, Co taken 6 times plus 2. You may need to refer back to the nomenclature section, but CO is carbon monoxide and the name for it is carbonyl. This is hexa, carbonyl, chromium. Now the charge on carbon monoxide is 0, so the total positive charge for the complex must come from chromium. That's simply chromium 2. Next we're asked to draw the electron filling arrangement here. So chromium plus 2, let's look that up. Chromium plus 2 is S0D4. Chromium 0 was S1D5. Chromium plus 2, S0D4. That tells us there's 4 electrons in the d orbitals. In an octahedral field, we have this arrangement that you see on the left. Now carbonyl is a strong ligand, and that means you'll have a large octahedral field splitting energy, which means that electrons will fill the T2G orbitals before they enter the Eg. So we're going to put all 4 electrons in the lower T2G orbitals. The electron configuration is written as T2G 4Eg 0. Its magnetic property will be described as paramagnetic. Its spin state, well, would be a low spin state. And the number of unpaired electrons, not asked in this question, but I'm asking it, number of unpaired electrons in this case is 2. Now all the answers to these problems are at the end of the chapter, so I won't do them all, but perhaps take a look at this third part here, Hg, H2O taken 6 times. Notice that water is often written as OH2 as a ligand. It's your option here. Hg, OH2 taken 6 times, charge of +2. Well, the name of this would be hexa aqua mercury. Water has a charge of 0, so all the charge must come from the mercury, so it must be mercury 2. Hexa aqua mercury 2. Now, water as a ligand is a weak ligand. And that means that there'll be a small octahedral field splitting energy. Next, we need to figure out the electron configuration of the metal cation. So mercury +2, S0D10. So the electrons, regardless of what kind of ligand is involved, whether it's small or large, they're going to fill all 5 d orbitals. The electron configuration will be written as T2G6 Eg4, 6 plus 4 is 10. Its magnetic properties be described as being diamagnetic. There are no unpaired electrons. And if I ask you how many unpaired electrons there are, you would say 0. Again, you can check the answer to the other one at the end of the chapter. Recall that when you have 4 ligands or 4 electron clouds around a central point, they will try and get as far away from each other as they can, and that arrangement is tetrahedral, about 110 degrees apart. The same is true with transition metals. These 4 black dots represent 4 ligands approaching the central metal cation in a tetrahedral environment. Notice that none of the ligands exactly lines up with any of the lobes in any of the d orbitals. And so there isn't as much repulsion created here in any condition. Now it's pretty difficult by inspection to say which of these 5 experiences the greatest repulsion. As it turns out, it's exactly opposite to what happens in an octahedral field. The 3 T2G orbitals which were least repelled in the octahedral field are most repelled in a tetrahedral field, and they're simply called T2 orbitals. The 2 Eg orbitals that were most strongly repelled in an octahedral environment are actually least repelled in a tetrahedral environment, and they're simply called E rather than Eg. So only 4 ligands approach the metal cation with tetrahedral complexes, compared to 6 ligands for octahedral complexes. The result is a smaller field splitting energy, for sure. And furthermore, the ligands that approach from the corners of a tetrahedron, well, none of them will directly be in line with any of the 5d orbitals. So less repulsion again. We can say that tetrahedral field splitting energy is much less than the octahedral field splitting energy. So this sounds like it's getting pretty complicated, but as it turns out, it's not so bad. Since the tetrahedral field splitting energy is so small, even strong ligands like cyanide are not able to cause low spin tetrahedral complexes to form. What we're saying here is that the tetrahedral field splitting energy is always less than the pairing repulsion. And thus, all tetrahedral complexes are found to be in a high spin state. They never pair up. They'll always spread out according to Hund's rule, just as if all the 5d orbitals were essentially degenerate. The energy difference is so small. And that makes it a lot easier on us. On page 194, there's an exercise for you to draw in the electron configuration of tetrahedral complexes of transition metal cations with 1 through 10 d electrons. Let's do maybe the first one together, and then I'll let you do the rest and just show you the solutions. So with 1 d electron, such as in vanadium plus 4, it'll fill the lowest energy orbital first. This is paramagnetic. It would be described as E1T20. The number of unpaired electrons is 1. If we had 2 d electrons, such as in a compound like titanium plus 2, we'd fill the lower energy orbitals first, still paramagnetic, E2, T20, and so on. Just keep in mind as you do this that all of the electron configurations are designated as high spin. Keep in mind that the field splitting energy of a tetrahedral complex is so small that all of the d orbitals will be singly filled before any of them are forced to pair up. And this is true regardless of the strength of the ligand, weak ligand or strong ligand. And so we say that the pairing repulsion energy is greater than the tetrahedral field splitting energy in all cases. So for sake of time, I will just show you the solutions to this exercise. You can pause the video as necessary to check your answers. Notice that in all but the case of 10 electrons in the d orbitals of the transition metal, the magnetic property is paramagnetic. In the case of a transition metal with 10 d electrons, only then is the magnetic property diamagnetic, with no unpaired electrons remaining. Page 194. As we just explained, 4 electron clouds can get as far away as possible from each other if they adopt a tetrahedral arrangement. However, there actually are some 4 coordinate transition metal complexes that adopt a square planar complex. Now there's no absolute rule as to which, when, and why, but in a general sense we could state it this way, that for transition metals that are smaller, and I'm talking about the 4th period, the first series of transition metals, scandium through zinc, these would be smaller than transition metals from the 2nd or 3rd transition metal series in periods 5 or 6. These are larger. So in the case of the smaller first series transition metals, the ligands will be closer together of necessity. And in such cases, they tend to form tetrahedral arrangements. But when we have larger transition metals from the 2nd or 3rd series, like gold or platinum, there's simply more space and less crowding. That's one consideration. Another consideration might simply be that a ligand such as ethylene diamine has limited distance it can stretch because it is joined together by an ethylene group. Square planar may suit that better. Whatever the case may be, and it's difficult to predict in every case, it turns out that it's a pretty simple way to handle it, as we'll see. Page 196. Let's look at a square planar 4 coordinate complex. Ligands in a square planar complex come in to the transition metal 90 degrees apart in a plane. The d orbital that would have the most direct interaction with a square planar group of 4 ligands would be the dx squared minus y squared orbitals. And here's what the energy level diagram looks like. So there is some splitting among the other 4 orbitals, but they're relatively close to each other in energy. And there is a relatively large energy gap between the dx squared minus y squared and all other d orbitals. So it turns out that the 4 lower ones are essentially, for our purposes, degenerate. The result is that in virtually all square planar complexes, the field splitting energy is very large. This field splitting energy is much greater than the pairing repulsion, such that all 4 low energy d orbitals will be filled before any electrons enter the high energy dx squared minus y squared orbital. Again, we can say the square planar field splitting energy is greater than the pairing repulsion, and this is true regardless of the ligand's field strength, whether it be weak or strong. And as a result, all square planar complexes are described as having a low spin state. On page 197, I have another exercise, an electron distribution chart for you to fill in. You can pause the video and check your answers against it. I simply want to point out that since the energy gap is so large between the dxy and dx squared minus y squared orbital, notice that the dx squared minus y squared orbital is not filled in any case until the other 4 orbitals are in fact filled. And that will give rise to a diamagnetic property state for a 4 coordinate square planar transition metal with 8 d electrons. Problem 17. Tetracarbonyl palladium-2 is found to be paramagnetic. Write its formula, draw an electron configuration of this complex, predict whether it is square planar or tetrahedral. Is this the normal geometry for a 4 coordinate second series transition metal complex? How many unpaired d electrons does it have? Let's work off to the right here. Tetracarbonyl palladium-2. It's a 4 coordinate complex. The formula would be transition metal first, followed by ligands. Carbonyl is carbon monoxide. Palladium-2. Now carbon monoxide has no charge, so the charge of palladium is +2. We have 8 electrons, 8 d electrons to fit in here. Let's fit them first into the square planar electron configuration box diagram. 8 electrons, 1, 2, 3, 4. Large energy gap, 5, 6, 7, 8. What's the magnetic property of this? Well, it's diamagnetic. And we're told that the complex is known to be paramagnetic. This has a low spin state. It has 0 unpaired electrons. This is clearly not an electron arrangement in tetracarbonyl palladium-2. Let's try the tetrahedral electron arrangement. 1, 2. Do we cross the gap? Yes. The tetrahedral field splitting energy is very small. 3, 4, 5, 6, 7, 8. The magnetic property for this is paramagnetic. All spin states are high spin states for tetrahedral arrangements. It has 2 unpaired electrons. So we can say that tetracarbonyl palladium-2 has a tetrahedral ligand arrangement. The last case for us to consider is that of a 2 coordinate complex, 2 ligands bonded to the central metal cation, such as diamine silver cation. When you only have 2 ligands, they're going to approach 180 degrees apart from opposite sides, as you see here. Which orbital of the d orbitals, in which of the 5 d orbitals would electrons in a d orbital suffer the most interference from ligands coming in 180 degrees apart. Can you see that it would be the dz squared orbital that has all its electron density directly in line with ligands approaching 180 degrees apart? So in fact, if you look at our energy level diagram, the dz squared orbital is most high in energy. The dyz and xz have some z component or area in the z region, the z region, so they would be repelled somewhat. The dxy and dx squared minus y squared have virtually no electron density in the z region. They would be least repelled. Again, this reduces to a very simple case, fortunately. These two coordinate transition metal complexes, which will be sp hybridized, two bonds, they only occur in the +1 ions of group 1b, such as copper 1, silver 1, or gold 1, which conveniently all have 10 d electrons. And they occur in +2 ions of group 2b, such as zinc 2, cadmium 2, mercury 2, which also have 10 d electrons. So it turns out that transition metals with only 2 ligands only form when the transition metal has 10 electrons in its d orbitals. And as a result, high or low spin states are just not assigned. The d orbitals will always be full. Let's take a look at problem number 19. For CuCN2-1, write its name, use a box diagram to show its d electron distribution, state its magnetic property. Here it is, CuCN2-1. Cyanide is -1, and there's 2 of them, so that's -2. Therefore, copper must be +1. Hence, the name would be dicyanocuprate 1. So copper +1 has an electron configuration. It's S0D10, as we just stated. There's 10 electrons, and they would likely fill in this order, filling the low energy orbitals first, and then moving to the high energy orbitals. But irregardless, since there's always 10, it doesn't really matter the filling order. The magnetic property of this complex will be diamagnetic. Let's talk about problem 20 before we close. Gold is mined by mixing with an aqueous solution of potassium cyanide to separate it. Finally, a practical application of this. To separate it from the ore as a linear cyano complex. And here's the equation for it. We have solid elemental gold being dissolved in the presence of cyanide to form dicyanoorate 1. Propose a reason why this chemical extraction works. Write the name of the coordination complex. Well, I just said it, but here it is. Now think about it. Gold is present as an element. It's quite inert and unreactive. It's not present as an oxide like many other metals. So one approach could be to, since it's so inert, one could dissolve all of the ore and just leave the solid gold behind. That might work, but in practice, think about it. Miners have to process literally tons of ore to get a very small quantity of gold. That would be a lot of dissolving of a lot of stuff and dirt. Wouldn't it make more sense to dissolve the small quantity, the gold flecks, and selectively remove it as solution and then filter out the waste material? And that's exactly how it's done. By way of a summary for crystal field theory, we saw that 4 different geometries can result. In the case of 6 ligands, the geometry is octahedral. Degenerate d orbitals are split as shown. With weak ligands, a high spin state results. And that's because the octahedral field splitting energy is always less than the pairing energy. In other words, a small split, and therefore all 5d orbitals would be singly filled before any pairing occurs. However, with strong ligands, a low spin state results. That's because the octahedral field splitting energy in such cases would be greater than the pairing energy, and these occur only when there are anywhere between 4 and 7 d electrons in the transition metal. Four coordinate systems are seen to be either tetrahedral or square planar. The field splittings are as shown. A tetrahedral field splitting usually occurs with small transition metals and large ligands, where space constraints are a concern. In all such cases, a high spin state results, and that's irregardless of the ligand strength. And that's because the tetrahedral field splitting energy is always small. It's less than the pairing repulsion, which means that d electrons will always fill all 5 d orbitals before they pair up. In the case of a square planar 4-coordinate transition metal complex, this usually occurs, and I say usually in parentheses, it usually occurs with large transition metals and small ligands where space constraints are relaxed. All result in a low spin state, regardless of the ligand strength, and that's because the square planar field splitting energy is relatively large compared to the pairing repulsion, and this is right here in the gap between the dxy and dx squared minus y squared orbitals. They're well separated. And finally, when you have a 2-coordinate transition metal complex, they are all linear. They only occur in transition metals with 10 d electrons. Because of this, the spin state is not stated, and of course they'll all be diamagnetic. So why are so many transition metal solutions and their complexes colored? Because they're partially filled, non-degenerate d orbitals are separated by small energy gaps, just the right size to allow their electrons to absorb photons of visible light and jump between orbitals. And so crystal field theory explains and to some extent predicts the colors and magnetic properties of transition metals and their complexes. And that concludes our study of transition metals for this course.